This is information for Unit 1, and what I have here is an example from a study that I did several years ago with college students. It was a sample of 307 college students, and they were all in romantic relationships. And I have this questionnaire that measured how happy or how satisfied they were in their relationships. And it had several items. For example, one of the questions here is it says, we have fun together, and they took that question and rated on a scale of 1 to 5, where 1 means much less than I want, or 3 is a little less than I want, and 5 is as much as I want. So they rated on a 5-point scale. And we have other items. We provide comfort to each other, as much as I want, less than I want, and so forth. So they rated each of these items. We have about 9 items there. And they rate each of those items on a 5-point scale. And then I added all those scores together, and then I divided by the number of items to get an average score on a 1 to 5 scale. So each person gets a score for their relationship satisfaction on a scale that ranges from 1 to 5. And now there's 2 questions that we can address when we're looking at the results for this scale. One question we might want to know is simply, well, where is the average score? On average, how satisfied are college students in their romantic relationships? And we could think about a couple of reasons why we might have different ideas about how happy they would be. I mean, maybe most college students are really happy in their relationships. Maybe college student romantic relationships are just wonderful, blissful relationships, and just about everybody reports having wonderful relationships with their partners. Or maybe on the other hand, college student relationships are really traumatic, stressful experiences. It's people that often haven't been together that long. It can be stormy relationships and people trying to figure out where they're going in life. And so there can be a lot of ups and downs and trauma and so forth. And so maybe college student romantic relationships are very stormy, stressful relationships. And maybe people in general have rather low satisfaction in relationships. Or maybe it's somewhere in the middle. So one question is simply, how happy or how satisfied on average are people in their relationships if we have a sample of college students? Another question is, how much are scores spread out? That is, are scores spread out really far so that you have some people that are really, really happy and other people that are very distressed? Or are they all close together? Maybe everybody's really happy, or maybe everyone's really distressed, but wherever they are, maybe everyone's kind of there as a big group and there's not much spread. So how much is it the scores are spread out so you have a big range of happiness, or are they all kind of clustered close together? And we can address these questions by the mean and the standard deviation. So we want to know, what is the mean and what is the standard deviation? So here is some output. This is from SPSS computer program. Software gives us output that looks like this. We'll frequently be seeing output from SPSS in examples in this class. And this output says, in this sample we had 307 people. The lowest score was a 1 and the highest score was a 5, which was also the possible range. The lowest possible score was a 1, the highest possible score was a 5. And the average, the mean, is 4.2 on our scale that went to 1 to 5. So that's a pretty high score. The average is pretty high. People are saying we are pretty happy and satisfied in our relationships. The standard deviation is 0.65. That's not very big. Scores are actually pretty close together. So it's a situation where pretty much everyone is saying we are very happy in our relationships. The mean and the standard deviation actually should paint a picture in your mind. When I say here's the mean, here's the standard deviation, you should be able to get a picture of what that might look like. Here I've put a normal distribution, and the mean, the center point, is right about 4.2 right there. And then the standard deviation, those arrows there tell you how far people typically deviate from the mean. So we can see that people typically deviate 0.65 units. And so the difference between here, these spans here, that's 0.65 units. And so most people are falling, that's a little bit higher than 3.5 right there, to just a little bit below 5. So people are pretty close together, all clustered together at the high end of the scale. In fact, think about, what if someone got a score of 3? In fact, maybe if you're in a relationship and you looked at that set of 9 items and you thought, hi, I think I will take the scale and see how happy I am in my relationship. And if you took those items and you responded to them and you summed your score and divided by the number of items to get your average score, and you said, well, my score is a 3. Well, if you got a 3, that's not good. It's at the middle point of the scale. You're right at the very midpoint of the scale, 1 to 5. But if you got a 3, in fact, I would bet if you got a 3, your relationship is not going to last much longer because a 3 is very distressed. If the data were normally distributed, which actually we know in this case we're going to fudge a bit because they're not, because you can see this normal distribution that we'd have people getting scores higher than 5 if the data fit a normal distribution, but that's not possible on our scale. So we know that technically this sample has data that don't quite fit a normal distribution. But for the sake of example, we could say if they were normally distributed, and we'll be making that assumption in other places as well, just say, well, what if they were normally distributed? But if they were normally distributed, we know that a score of 3, there would only be about approximately 2% of people falling lower than that, because that's a z-score. You're about 2 standard deviations below the mean. And if you recall the cutoffs for what percentages fall at various points along a normal distribution, you know that only 2% of cases fall less than 2 standard deviations below the mean. So you're at about the 2nd percentile. You have a very low level of satisfaction. Even though 3 isn't the midpoint of the scale, that corresponds to a very distressed person. So most people are near the top. Most people, and they're fairly clustered together, which, by the way, that actually makes sense. There's a couple of reasons why that's true. One is that in relationships in general, whether it's dating relationships or marriage relationships, people tend to have a positive, optimistic bias when they talk about their relationship. It's just common for people to say, well, I think our relationship's just a little bit better than average. So it's very common for people to report very high levels of happiness and satisfaction in relationships. Another thing why this is especially true for a sample of college students is that, and this might sound hard to believe if someone's experienced a recent breakup of a relationship, but if you're in a college student, it's relatively easy to break up, at least compared to other more committed relationships, compared to, for example, if you're dating and not living together, a couple who's living together, it's harder for them to break up than those who aren't living together. And if a couple's married, it's harder for them to break up. And if they have children, it's even harder for them to break up. And so the more that there's constraints on breaking up a relationship, the more people are likely to stay in that relationship, even if it's distressing. And what that means, if a student's in a dating relationship, we have college students, mostly dating relationships. Maybe these relationships, some of these haven't been going that long. But at that point, if you're in a relationship and it's not going so well, and you're thinking, well, I'm not sure I'm all that happy in this relationship, you're likely to leave the relationship. So what happens is that once relationships get just a little bit unhappy, people leave and they stop the relationship. So for those reasons, it's very common to have very high levels of satisfaction reported in college student dating relationships. Okay, let's look at something else that I might have you do with the same output here, and that is I might ask you to give me a written summary of the results. That is, I want you to give me a written summary of the mean and the standard deviation, and I have a particular way I would like you to give that summary to me, and part of what I'm looking for here is a summary that helps me see that you understand what these scores mean and what they do for us. And also a summary that conveys important information to the reader so that you get practice writing results so that readers can understand what you're writing about. So in this case, I'm going to talk, the first thing I'm going to clarify is what type of scale. We're going to report a mean and standard deviation for something. A mean and standard deviation for what? What are we talking about here? We're talking about a mean and a standard deviation for a satisfaction scale. So I'm going to start out by saying on a satisfaction scale, I'm going to name what type of scale this is, what this variable is that we're looking at. And then I'm also going to give the range of possible scores. The lowest possible score was a 1, and the highest possible score was a 5. Recall that people rated their scores on a scale of 1 to 5, and then I averaged all their responses together to get a single score for a person. So if they responded 1 to everything, then they would get a 1. If they responded 5 to everything, they'd get a score of 5. So the scale ranged from 1 to 5. And on the scale, it ranged from 1 to 5. The average score was 4.2. or 4.20. One thing I'll mention here in a moment is that when giving values like that, I like you to round to 2 decimal points to make everything consistent. So I've rounded to 2 decimal points, 4.20. So I've named the scale, I've given the range 1 to 5, and I've given the average score. And those are the things I want you to do to summarize the mean. Then for the standard deviation, I want you to give me the standard deviation in a way that shows you understand what a standard deviation is, that you understand that a standard deviation tells you how far on average people deviate from the mean. So if our standard deviation is 0.65, that means on average people typically deviate from the mean of 4.2 by 0.65 units. And note that that's what I have down here. On average, people deviated from the score from 4.2 by 0.65 units. So that's a way that both tells the reader what the standard deviation is, it's 0.65, and also clarifies you understand conceptually what that value means. And that's how to give a written summary of a mean and a standard deviation. A couple things to note when you do those summaries is that when you give the name of the scale, and I mentioned I want you to name the scale, tell me it's a satisfaction scale in this example, or whatever variable it is, give me the name of the variable, and I want you to name it using normal English words. And the reason why I mention that is because sometimes you will look at output like this example down below now. Note that it says SAT 24A. And you might see output that looks something like that because when we do analyses and put variables into computer programs and software to run our analyses, we often need to give those variables names, and it's often certain. We maybe have a lot of variables. We need to think of names for everything, and we might have space limitations for what we're going to name them. And so what we usually end up doing is giving them kind of these cryptic code names. So I might have a variable that in my computer program I call it SAT 24A, and when I run my analysis, it'll say here are the results for SAT 24A. But when you give me a written summary, I want you to give me a written summary that someone could read and understand what you're talking about. And if you say SAT 24A, your reader is not going to know what you're talking about. So a key thing is when you give written summaries, do not put abbreviated computer program labels into your written summary. Give me normal words. So you could say on a satisfaction scale, but don't say on scale SAT 24A or whatever your cryptic code name is. Do not put that in your written summary. And like I mentioned just a moment ago, I have down here, round everything to 2 decimals. Now you don't need to round the 1 and the 5 because those are just even numbers, but you can, but all the other values when you're giving statistics round to 2 decimal places. So I've rounded the average score and I've rounded the standard deviation as both been rounded to 2 decimals, although it's already been rounded that way also in the output. But if it's not rounded that way in the output, still round it that way in your written summary. What else could you do with this output? Well, another thing that I might ask you to do is to compute these sums of squares. This is actually working backwards from how we usually compute a standard deviation. Usually if I want you to calculate a standard deviation, or if you need to calculate one, the first step is to calculate the sums of squares, then you calculate the variance, and from that you can calculate the standard deviation. I might say, hey, let's go backwards, and I'll give you the standard deviation, and you go backwards and tell me what the sums of squares was behind it. And so we can simply do that by first taking our standard deviation, 0.65. So here's our standard deviation, 0.65. And the first thing to do is we want to calculate the variance. And if we take our standard deviation and square it, we have a variance. So the variance is 0.4225. 0.65 squared gives us 0.4225. And then once I have my variance, I can now multiply the variance by my degrees of freedom. We have 307 people in our sample. Degrees of freedom are n minus 1, so our degrees of freedom are 306. So I take my variance times my degrees of freedom, and I get 129.285. So that would be our sums of squares, 129.285. Another thing I might do is that I could say, here is our mean or standard deviation. Let's take someone from this sample. Let's say I have a person named Electra, and she got a score of 3.72 on the satisfaction scale. If that is her score, what is her z-score? How would you calculate or compute her z-score? Well, to calculate her z-score, we need to know what her score is. X, we'll call her score X. X bar, that's the sample mean, and the standard deviation. And so she got a score of 3.72. So that goes right there. And X bar, that's our sample mean, 4.20. So plug that right there. Standard deviation, 0.65. Plug that in down there. So I've got her score, X minus X bar minus the sample mean, divided by the standard deviation. And I get a z-score with a bit of rounding of negative 0.738, or we could round even more, say negative 0.74, meaning she is 0.74 standard deviations below the mean. She's below the mean, not a full standard deviation below the mean, not quite a full standard deviation below the mean, but 0.74 or 0.738 standard deviations below the mean. That's how we'd interpret her z-score. So we've got Electra, she's got a raw score of 3.72. We've calculated that her z-score, therefore, is negative 0.738 or negative 0.74 with a bit of rounding. Then we could say, well, what is the probability of her scores? Like, for example, what is the probability that you would randomly pull someone from the sample and get someone with a score that is lower than Electra? And again, we're going to start doing that thing where we're going to assume that we have a normal distribution and we can answer these questions about probability. So if the data were normally distributed, what is the probability of getting someone with a score lower than Electra? Now, there's a couple ways we could address this question. One way is just off the top of your head, for memory, you should be able to give me a range of where this probability is going to fall. Because if you've memorized these cutoffs along the normal curve, if you memorize the percentages of cases that fall within the even standard deviation units, you know that 2% of the cases fall below 2 standard deviations below the mean or lower, that 14% fall between -2 and -1, or altogether 16% fall below -1 standard deviation, and so forth. Or we know that 84% fall below 1 standard deviation above the mean, and 98% fall below 2 standard deviations above the mean, or 2% are higher than 2 standard deviations above the mean. So if we know all these cutoffs, and hopefully you have memorized these, or if you haven't memorized them yet, that is a task to do, to memorize these so you can recall these cutoffs. And so if we know that her z-score is negative 0.738, not quite a full standard deviation below the mean, but close to it. So it's right about where this arrow is right about where she scores right here, getting close to a full standard deviation below the mean. And we know that if she was a full standard deviation below the mean, then the probability to get a score lower than that is 16%, but she's not quite a full standard deviation below the mean, so it's something a little bit bigger than 16%. We know that if she was right at the mean, the probability to get a score lower than that is 50%, and she's less than that, so it's something that's going to be less than 50%. So we know it's somewhere between 16% and 50%. And you should be able to just to do that just off the top of your head, because you should have these cutoff values memorized. Now, there's a couple different ways I might ask questions about probability. I could say, what's the probability to score lower than, say, negative 0.378? Or another situation is I might give you maybe a higher score, like say give you a score, someone gets a standard z-score of 1.2, and I might say, what's the probability of getting a score higher than that? And these types of questions I will always ask in the direction of going towards the tail. So I'll give you a low value and say, what's the probability of getting a score lower than that? Or I might give you a high value and say, what's the probability of getting a score higher than that? So that's one type of question. Another question I might ask is, what's the probability of getting a score more extreme than something? And when I say more extreme, I mean in either direction. So if I were to say, what's the probability of getting a score more extreme than negative 0.738? What I mean is the probability of getting a score lower than negative 0.738 or higher than positive 0.738 in either direction. The probability of getting a score lower than negative 0.738 or higher than positive 0.738. And it's actually fairly easy to go from a one-tailed probability to a two-tailed probability, is that you simply double it. So whatever we had for going to probability going in one direction, it's just double for going in two directions. So if I ask the question, what's the probability of score more extreme than negative 0.738, we can just take 16%, double it, get 32%, 50%, double it, we get 100%. In other words, we know it's somewhere, just for memory, we know it's somewhere between 32% and 100%. Not very precise, but it gives us a range that we know just off the top of our heads. Now, another thing that I might do, and this is something that I will, when I ask this, very frequently I want you to know this from memory, off the top of your head type of thing. And that is, rather than giving me a probability of getting a score higher or lower, to give me someone's percentile. So if Electra got a score of negative 0.738, a z-score, what is her percentile? And again, we know, given these cutoffs here, and one thing we always want to clarify when we're doing this, we're going to assume that we have a normal distribution. So we're going to say, assuming the data are normally distributed, what is her percentile with a z-score of negative 0.738? And we know that her percentile would be at the 16th percentile if she had a z-score of -1. It would be at the 50th percentile if she had a z-score of 0. So we know her percentile is somewhere between the 16th and the 50th percentile. So these are all things, what I've been doing here is examples of where you might figure out a probability or figure out a percentile just from memory without actually using a z-table. There's some times, though, where I want you to give me a precise value, and for that, you will need to use a z-table. Now, actually, the truth is, these z-tables are actually not very useful anymore because today, if you wanted to look up a z-value, if I wanted to look up a z-value for something, I wouldn't go pull up a paper table to look at. There's lots of apps, or you can just go to Google and you Google Z calculator, and you'll have all types of online calculators that will pop up. There's lots of apps and calculators available out there that you could quickly pull up, and you type in your Z value, and it'll immediately pull back your percentage or percentile or whatever you're looking for, and it can be done very quickly. So if I really wanted to get a Z value and a percentile or a probability, I would use one of those apps or one of those calculators for it, and not a piece of paper. But it's kind of hard to use apps and calculators like that on a test. And so one of the things that these types of z-tables are very useful for are classes like this one, where I plan to give you a test and might ask you a question where you need to look up a precise z-value. And it's also something that I would suggest you use this table on your homeworks. There should be a copy of this table on Canvas, so you can use the same table for homeworks that will match the table I will use that I would give to you if I ask you a question like this on a test. So this is a z-table that we can use to get probabilities of different z-scores that would fall along a normal distribution. And again, we're assuming we're dealing with scores fitting a normal distribution. Let me zoom into this table, and here I have z-score. If Electra had a z-score of negative 0.74, rounded out a bit, and we can say, what is the probability of getting, say, a score lower than negative 0.74? And so in the z-table, we can look up z-score 0.74. And this table gives us a few different options for types of probabilities we might want to get. For example, what percent of cases are going to fall between the mean and that given z-score? That is, the mean between the 0 point right in the middle and the z-score, whatever it is, how many cases fall in between those 2 points? Or we can ask the question, what percent of people, what percent of cases will fall in the larger portion of that tail? Or we can ask, what is the percentage of cases that will fall in the smaller portion of the tail? And that's the type of question I'm always going to ask you. I'm always going to say, if I give you a high number, I might say, what's the probability of getting a score higher than this? Or if I give you a lower number, ask, what's the probability of getting a score lower than that? Which are all questions that are going towards the tail. So for this class, all the questions will pertain to this column right here, the smaller portion. Now, when using a z-table, one thing to keep in mind is the fact that a negative z-score, the distribution for the negative values, is just a mirror image of the distribution for the positive values. So the probability of getting a score lower than a negative z-score is the same as the probability of getting a score higher than the positive version of that same score. So the probability of getting a score lower than negative 0.74 is the same as the probability of getting a score higher than positive 0.74. And to save space, people usually just print the positive values and don't print a separate table of all the negative scores, because that would just be redundant. It would be the same table except for just be a bunch of negative values. And it's a lot easier just to know that the negative and the positive are just a mirror image. So if I ask you what's the probability of getting a score lower than negative 0.74, the first step is to flip that around, and we're going to say, what's the probability of getting a score higher than positive 0.74? And then we look that up on the table. We go to the z-score 0.74. We're going in the tail, a smaller portion. It says 0.2296, or with rounding, we can say 0.23. In other words, 23%. Our probability is 0.23, or we can say it like this: 23% of the cases will have scores higher than a z-score of 0.74, which means that 23% of the cases will fall lower than negative 0.74. So the probability of getting a score lower than negative 0.74 is 0.23, or 23%. Now, if I ask the question about being more extreme, what's the probability of getting a score more extreme than a z-score of negative 0.74? That's going in either direction, and we simply take the probability going in one direction and double it. So 0.2296 times 2, we get 0.4592, or with rounding, 0.46. And that would be the probability of getting a score more extreme than negative 0.74, going either direction. That's lower than negative 0.74, higher than positive 0.74, more extreme in either direction. And the next thing I want to talk about is how would you give a written summary about someone's z-score. And again, I have a template that I would like you to follow if I ask you to give me a written summary of a z-score. And it goes like this. Again, we're going to name the scale. In this case, it's a score on a satisfaction scale. We want to name the variable. And then I want you to talk about the z-score in a way that shows you understand what the z-score means and tells me what the value is. So she got a z-score of negative 0.74. I want you to give me that value, 0.74, but also do it in a way that clarifies you understand that it's telling you how many standard deviations above or below a mean a person's observed score actually fell. Her score is negative, so she was 0.74 standard deviations below the mean. So that's what we have here. Electra's satisfaction score was 0.74 standard deviations below the mean. Then I want you to give me her percentile. And for the written summaries, most likely I'm going to want you to do it from memory, where you don't have a table, not looking it up, not using an app, just off the top of your head. Give me the range where her percentile is going to fall. And we're going to preface that by that if satisfaction is normally distributed, again, that's an important thing to state, because if it's not normally distributed, this doesn't work. And as I noted, that in this case, the scores probably actually aren't normally distributed. So we've probably violated that assumption for this example. But we're going to use this example anyway and assume, we're going to say, let's assume they're normally distributed. And I might note that although this example, they're probably not normal in truth, there's a lot of situations where you would be working with scores that have a normal distribution, especially anyone who goes or is doing, say, clinical work, or working in, say, school psychology. If you're doing assessments such as personality assessments or intelligence or cognitive assessments, a lot of those instruments are designed to have scores that fit a normal distribution. So all these things work very well in those types of situations where you might be doing assessments in some kind of applied setting. Another thing that's also useful for this type of example of assuming things are normally distributed is that later on in this course, we're going to be talking about other types of distributions that we can have confidence that they actually do fit a normal distribution or have a known distributional shape. So this is actually setting us up for things we're going to be doing in the future in this course, where we can safely assume a normal distribution. But for now, we're just going to assume that, even if we're fudging a bit here. But it's important when you write it, say, if satisfaction is normally distributed. So you clarify that you know that we're assuming it's normally distributed. This whole thing is based on that assumption of a normal distribution. So if satisfaction is normally distributed, her score is between the 16th and the 50th percentile, which is what we looked at before. If we looked at those cutoffs based on the memorized points. If you're one standard deviation below the mean, you're at the 16th percentile. You're at the mean, you're at the 50th percentile. She's in between those 2 points, so her percentile is somewhere between the 16th and the 50th percentile. And that is how to give a written summary of the z-score. And that is everything that I have right now for Unit 1.